Astrophysics. We are going to build an in-body simulation, an in-body numerical calculation. So you may have seen the 3-body, but what about 4, about 5, what about however many you want? So I'm going to go through how to build this from scratch in Python. It's not the best model, okay, but it works, and it's easier to understand. So you can make more sophisticated models if you want, but I like to make things that are, you can see everything. That's the goal here, to really understand the basics. So let's think about the 3-body problem. So imagine I have 3 masses here, and they're all gravitationally interacting. Well, in order to calculate the force on each one, I need to calculate 3 forces, right? So I have the interaction between star 1 and 3, between star 1 and 2, and between star 2 and 3. And so each one of those interactions has 2 forces, right? So 2 pulls on 3 and 3 pulls on 2, they're equal and opposite forces. So I only have to calculate those things once. But I'm going to calculate all of the forces by finding the vector position, relative position from 1 to 2, 2 to 3, and then 3 to 1. I like to do it in order like that to keep track of things. And then I can calculate the gravitational force as negative the gravitational constant g, m1, m2 times r1, 2 hat, right? That's that vector in the direction of that, divided by the magnitude squared. Once I do that, I can calculate the net force on mass 1, the net force, right? So that's going to be both those forces added together. And then I can break the motion into short time intervals. During each time interval, I'll update the momentum from the momentum principle. I'll update the position from the definition of average velocity. And then I'll do that for all 3 stars and just do it again and again. And now the problem is, if I wanted to do 4 masses, let's just add a 4th mass in here. So suppose I have mass 4 right there. Then I have to calculate this interaction, this interaction, this interaction. So I actually have 3 more interactions by adding that 1 mass in there. If I have a 5th mass, you can see that things start getting out of control, right? I'll probably even miss. Yeah, I think I got them all. So I'm going to have to calculate all those interactions. Things can get out of hand very quickly computationally, but also just keeping track of all the names is really difficult. So we don't want to individually name the different objects. We're going to put them all in a list. So we got a lot of work to do. I think we should just jump right into Python and get started. It's the same idea though, right? We're going to use the same idea of calculating the interaction between all the masses, but we're going to do it automatically instead of doing it manually by saying, oh, 1, 2, 1, 3, 1, 4th, and so forth like that. Okay, let's just get started. I'm going to use non-real units. I'm going to use G as, let's say G is 1. We'll change that later. M is 1. R is 1. Let's just use everything as 1 just so we can have useful units and not have to deal with all the small numbers. But okay, I'm going to get started jumping over here to Web v Python. I have a blank slate. Okay, let's just get started. I'm going to make mistakes, and that's okay. So I'm going to give him my constants. G is 1, M is 1, R is 1, and that's fine for now. I'm going to let's start off with just 5 objects, just because we can see what's going on. So I'm going to say, this is the way I like to do it. I'm going to have a counter number n, and then I'm going to have a max number n, right, capital N. And then I can make a list of objects, my stars. I'm going to put them in a list. So I'm going to give a list of stars. Stars is an empty list. And I want to go through and just add a bunch of stars to that list. I'm going to put them in random locations because that's just fun. So while n is less than n, I want to go through and make a random vector. So my random vector is just going to be r. I'm going to call it RT. It's r times the vector 2 times random minus 1, 2 times random minus 1, 2 times random minus 1. So random is a function in Web v Python that returns a number between 0 and 1. If I take 2 times that, it's between 0 and 2. If I subtract 1, it's between -1 and 1. So this is going to put my stars in a box that's -r to r. And if I want to change the value of r, it works fine, but there's my vector. And if you want to, like, do some type of cutting and put it into a sphere, that's fine. It doesn't really matter. I'm just going to use a box because I don't have that many anyway. Now I'm going to use that RT to make a sphere. And that sphere is going to go in my list of stars. So stars is equal to stars, not stars, stars plus the sphere. So I'm going to put the sphere as a list. So I have a list of sphere of objects. So sphere, the position is going to be equal to RT. The radius is going to be equal to, let's say, R over 30. I'm just picking a value right there. I do want to put some other things in here. We're definitely going to want to make trail equals true, but let's just leave the rest for now. And then I'm going to add 1 to my counter, and I should get 5 stars at random locations. And there they are, 5 stars, see? And they're just around, and every time you run it, you get something different. Okay, now we need to practice traversing lists. We want to go through the list and do stuff. So let me just show you 2 ways to traverse the list, and we're going to use both of these methods. So the first way is to just say my favorite. So suppose I want to go through and print the position of each star. So I can do that. I only have 5, so I can do that. So the first way I can do that is with for star in stars. This is my favorite. So this takes the list of stars and it goes through each item and it calls that item star, or whatever I want to call it. I like to say stars is the list and star is the element, and it just makes sense, right? It's like English. And now I can just do whatever I want to star. So print star.pos. So it's going to go through the list, call each one star, and then print its position. See? Isn't that nice? Okay, now there's another way to go through the list, and this is very useful. So let's just delete this. For I in range length, let's just do this. I want to show you something. Print length of stars. So length is a function in Python. When you give it a list, it returns the length of that list. So if I run this, I get a length of 5. Okay. You could use n, but I'm going to use length. And now watch this, print range length of stars. So range tells you, well, I'm surprised, I thought I'd give you the whole thing, but it starts at 0, it goes to 5, and it has an increment of 1. So this is going to make a list from 0 to 5 and call each one a number. So let's just print, watch this. For I in range length of stars, print I. So it's going to print the values of I for each one, which is not the item in the list, right? We're just doing a for loop. So 0 through 4. So that's my first item, my last item. There's 5 items total. Now I can use that I index to print stars I, that's the ith element, .pos. So this will give me the positions of all the stars just like before. Same thing. Different thing because they're random. Every time I run it, they're different. Okay. So we have those 2 ways to traverse the list of stars. Now, I do need some things in here. I need to go through and give the stars a mass. I need to give them a momentum, because if I'm going to change their mass and their momentum, I need to do that. So let's traverse the list in the simple way for star in stars, and let's give them a mass. I'm going to give them all the same mass. So star.m equals m over n. I'm going to do that because that way I don't increase the total mass of my thing. M is the total mass of all my stars, okay, or planets or asteroids or whatever you want to call them. So if I have more stars, my total mass stays the same. Star, I'm going to start all of these with some initial velocity. Did I do that before? What did I do before? I gave them an initial velocity in just one of the directions. Let's do that just for fun. So star.p is going to be star.m. It's the same element in that list, right? Times the vector 0.1 times 2 times, I got to put this right here, times 2 times random minus 1. So that's the x coordinate, and then the other 2 will be 0. Is that what I did before? No, I didn't, but that's fine. So they're just going to be moving around. It doesn't really matter. I do want to do one other thing. I want to give it one other property, and that's the force. So I'm going to assign the net force as a property of the object. Star.f equals vector 0, 0, 0. And I'm going to add to that. But star.f, even though f is actually a property of the interaction, I'm going to call star.f a property of the star. It's the net force on that star. Okay. Now I'm going to also need t equals 0 and a time step, dt equals 0.01. Okay. So we're pretty much ready to go through and start doing some serious calculations. So let's make a while loop over time. Let's run this for 10 seconds. So while t is less than 10, rate 100. So rate 100 says don't do more than 100 calculations per second, and that will make it run in real time. You can change that; it's not a big deal. And we're gonna set this up, and then we're gonna do some cool stuff after that. So the first thing I need to do is to go through each element in my stars and calculate r with respect to other stars. Okay, so I'm going to actually do a double traverse because I need to take each star and how it interacts with every other star. So let's do this for I in range length of stars. That's going to go through the I element, and then I'm going to do this for j in range length stars. So this double loop is going to go through basically all my combinations of I and j, right? So if I have star 1, 1, star 1, 2, star 2, 1, 3, and so forth, I do all my combinations, and that's kind of cool. Now, the first thing I want to do actually is up here. I'm going to calculate the force on each object and add it to the net force. But I need to set my net force to 0 before I do that, because every time I go through the loop, I'm going to recalculate the net force. So let's go through and say for star in stars, star.f equals vector 0, 0, 0. So now when I add my forces to that, it starts off at 0. Otherwise, the forces would just get bigger and bigger and bigger and bigger. But now I have these two elements, I, j. What I don't want to look at R11. I don't want to calculate the force on star 1 due to star 1 because that's infinity, right? Because they're right on top of each other. They can't push on itself. So what I'm going to do is to say if I not equal to j, then we're going to do this. But if I is equal to j, don't do this. So the first thing we're going to do is to calculate rji. I get this backwards. Let me just check to make sure I don't get this backwards. Rji is going to be stars I dot POS minus stars j dot POS. Right? And I and j cannot be equal to each other. Now I can take that vector and calculate my force and add it to the net force. So I'm going to look at star I. Stars I. This is the force on I. Stars I dot F is going to be stars I dot F minus G times stars I dot M times stars J dot M, right? I have two masses times norm Rji divided by mag. Can you see this? Let's see. Let me just put some spaces down here. Well, mag, I'll show you in just a second. Mag Rji. And that should be it. All right, so there's my old force, and then I'm adding on this new force. I'll go through all the stars and do that. And then after that, I'll have all my stars' net forces calculated, because I can go through all the I's, through all the J's, and I get all the forces. Now, I am double doing, right? If I did the three-body problem, I could just calculate the force 1 on 2, and I don't need to do 2 on 1. I'm doing both of them here just because it's a little bit logically easier. Now that I have the force, I can update the momentums. I'm almost done. So let's dedent over here and go back and update the momentum, update the position for all the stars. For star in stars, see, I don't need to index the I. The only reason I need to do that so I could see how they relate to all the other ones. star dot p equals star dot p plus star dot f times dt, and then star dot pos plus star dot p times dt divided by star dot m. And then I need to update time. T equals t plus dt. I think that should work. Okay, let's just see if this does indeed run. Okay, so they don't look like they're moving, but it could be that the mass is too... Oh, undefined object evaluating star j.pos. Okay, maybe it did star j, so that's down here. Minus star j, stars. Simple little error. There we go. Okay, I'm gonna increase the number of things, and then I want to run this because I want something to happen that hasn't happened yet. That looks pretty cool. Let's let it run for a little bit longer and see if. And this is 3D, right? I'm looking for an explosion. Okay, it didn't happen. Let's increase the number of stars to 10. And I'm going to go over here to make trail. And I'm going to say retain equals 100. So if you just do make trail, it will leave literally a point behind the object as it moves around. But I don't want to keep those forever just because it gets a little too messy. This will make it look a little bit better. So run this and let's see what happens. So now I have a bunch more stars. And they're well behaved. I'm really kind of disappointed at that. Fine, I'm going to increase this to 50 stars. I want something bad to happen, because bad things can happen. But it is pretty cool, right? Okay, here we go. That's still behaving quite well. Maybe because my masses are too small. Let's just increase the mass to 10. Let's see what happens there. Okay, there we go. That's pretty good. So what's happening is that it's possible that two stars can get super close to each other, and so close together that the force between them is super, super high, and during that short time interval, they have a large change in momentum, and they just get ejected, and they get shot out into space. Okay, so we can fix that. We can fix that, and that's a common way to do it is with a softening parameter. So let me switch to the board here and change our calculation a little bit. So here's the force, right? And imagine that I have two objects here and there. And this is, we'll just call that R12 right there. And if that R gets too small, this force gets too large, and weird things happen. So what I can do is to add in a parameter here called R softening. So I'm actually going to write this as this plus RS squared, and then R12. So I just have the same thing. I'm just going to add in this softening parameter, and let's say R softening is 0.01. And so what this will do is if this went to 0, that's not 0, that's a constant number, and it will never go to 0, so you'll still have a force that doesn't get too big. Now, as R gets really big, that number really doesn't do anything. So it really only comes into play at very small distances, and it should make things behave better, which I'm surprised we didn't have any misbehaved things over here, but maybe it's because my momentums were, I think that's what it was. If I put this star, I'm going to put this at 0. I think this will make it, vector 0, 0, 0. So they all start at a velocity of 0. Yeah, see, there you get these explosions, right? So those two things got so close together, they got ejected. Why didn't that happen before? Because they had momentum, so when they have momentum, the angular momentum is going to keep them from getting too close together, which is kind of cool. Now, let's just run this again with an R softening in here. And then I'm going to do one more thing. So up here, I'm going to say, let's put this at 1. Let's put this at R soft. Let's call it, R soft is 0.01. So then down here, when I calculate the force, I have G, M1, M2, And then I have the mag of r. Oh, I didn't square it. Huh, that's why. Squared. Let's run that again. That's why it wasn't getting ejected. So now you really get some problems there. You see that? Okay, bad. If I go down to the force, I'm going to add in that r softening. So this is going to be the magnitude of ri squared right there. And then I'm going to add in r soft squared plus r soft squared. And that was what I called it, right? Yep. Okay, so let's run it again and see if we get any explosions. We do, right? But they're not as bad. And if I increase that parameter, let's put that at, see, they're not even running away. They're going to come back. Let's put that parameter at 0.2. These are things that you just have to play around with. They're getting close, but they're behaved much better behaved. And you can turn off these trails. I'm going to put really short trail. No, I'm going to leave it. Okay, so I'm pretty happy with this whole thing. I do want to do one new thing. I want to model, and I think I'm just going to turn off the trails. And let's run it right there. Yeah, that looks good. So imagine this is like a giant cloud of dust, and it just gravitationally attracts and shrinks down, and then it explodes back up, and it kind of does this in and out, which is pretty cool. But what if the little cloud has a slight rotation to begin with? So let me switch to the board and show you how we can put that in here. And this would be modeling a solar system. Now we do have some problems to think about, but it'll be a basic model. So suppose that I take my masses. So here's my masses. And I have some axis of rotation. And so they're all rotating with an angular velocity omega. And let's put this omega in the y direction. So I'm going to write omega as a vector, 0, 0.010. So it's a vector. Each one of these will have an rxy vector, or it'd be rxz vector. And so I can calculate the velocity based on it moving in the circle. Velocity, I'm going to call, it's going to be, is it omega cross r? It's omega cross, yeah. It's going to be omega cross r, and this is going to be xz. So that's the vector in the xz direction. I don't care about its y value. But now I can find the velocity for each one, and I can use that to find the momentum for each one. So the whole thing's going to be rotating a little bit. Let's see what happens in that case. It's going to be awesome. Okay, so let's give it an omega. Omega is going to be the vector 0, 0. What did I say? 0, 1. And then down here, when I go find their velocity, it's going to be the mass times the cross product of omega. And then I need the vector. I'm going to write this as the vector r star dot pos dot x 0. I don't care about the y value. Star dot pos dot z. So now they'll all have some velocity. They should be moving in a circle. Let's just see what happens if I do that. Are they rotating? I think they are rotating. And you know, this actually is a pretty nice way to show that solar systems get flat, because as the thing collapses, you have this gravitational force pulling towards the center. But if you think about it in terms of circular motion, there's a centrifugal force pushing away. Let me increase that softening parameter a little bit higher to 0.03. Let's put this at 100. And let's run it again. So is it rotating? It's hard to tell. Let's increase the rotation rate. That's the nice thing about these parameters, right? I can just play around with it and just do whatever I want. Okay, is this rotating? Yes. And so as it rotates, angular momentum means it's going to rotate faster as the whole thing collapses. I think I need to increase my rotation rate. That one's rotating pretty good right there. And then looking at it from the side, is it flattening out? I don't know. It's hard to tell, but we could increase the number of points. I think it's doing pretty good. Solar system, yeah, I'm pretty happy with this. And because of that softening parameter, when these things get really close together, they kind of just like orbit each other and they kind of get stuck, which is nice. You look at these two masses stuck together and they can't go all the way together and they just end up like that. So we could do a whole bunch of things. I'm not going to, but you could plot the angular momentum as a function of time, the total momentum, the energy. There's a whole bunch of things you could do with this in-body program. You could see how big it could get. I'm not going to do that right now. I'm going to stick at 100. But there you go with the in-body program. The link to this code will be down below. Hope you enjoyed that. That was fun. I'm going to play with this some more, and I'll talk to you later.